Hello. In this video, I will discuss in detail about normed vector spaces and delve deeper into the subject matter, more specifically about matrix norms and some series of matrices. As a basis for discussion, I will consider the following exercise. The space E MP of an R of square matrices of order P with real coefficients is equipped with the norm defined for any matrix A equal to H by the infinity norm of A, which is the max over Ij of the absolute value of Ij. First question. Show that the norm of the product AB, the infinity norm of AB, is bounded by P times the infinity norm of A times the infinity norm of B for any matrices A and B. Second question, show that the series of matrices with general term 1 over factorial NA to the power of N is convergent in this space MP2R equipped with the infinity norm defined here. Third question, we now equip MP2R with a norm N that satisfies the condition that the norm of A times B is bounded by the norm of A times the norm of B. This is what is called a matrix norm or submultiplicative norm. Assume that M is a matrix whose norm is strictly less than 1. Show that the matrix I minus M is invertible. Deduce that the series of matrices sigma from N equals 0 to infinity of M to the power of N is convergent. In MP2R1, this norm, N, is calculated. It comes out by the first question as posed to us. Show that the norm of the product AB, the infinity norm of the product AB, is bounded by P times the infinity norm of A times the infinity norm of B. Let's call this product C. We will therefore set AB equal to C or CG. We know that CJ is equal to the sum from K equals A to P of I, K, B, K, J. This is the product of matrices A and B. Thus, the infinity norm of the product AB corresponds to the infinity norm of C. By definition, it is the max over Ij of the absolute value of Cij, or the max over Ij. Of the sum, or of the absolute value of the sum sigma, from K equals 1 to P of Ik Bkj. Then we can bound the absolute value of this sum by the sum of the products of the absolute values. Thus, we obtain the max over Ij of sigma from K equals 1 to P of the absolute value of Ik times the absolute value of Bkj. We will now bound each term Aik by the max over Ij of Aij, and each term Bk, J by the max over Ij of the absolute value of Bij. So each sigma is bounded by a sigma of the product of max. These sigmas are therefore the same, and the max is one of them. It is no longer necessary to keep this max in the bound. Since the max is the same, this sum is nothing other than P times this max, which is nothing other than P times the first max, which is the infinity norm of A, and the second max is the infinity norm of B, and we have indeed established that the infinity norm of A times B is bounded by P times the infinity norm of A times the infinity norm of B. Second question, show that the series of matrices sigma from N equals 0 to infinity 1 over factorial NA to the power of N is convergent. To do this, we will try to bound the infinity norm of A to the power of N. We will do this by induction. Let's first look at what happens when N equals 3. We have the infinity norm of A cubed. We can write that it is bounded by P times the infinity norm of a squared times the infinity norm of A. It suffices to set A3 equal to A2 times A and use the infinity norm of the product bounded by P times the product of the infinity norms. Now at this stage, the infinity norm of A2 is in turn, according to the same relation of dou bounded by P times the infinity norm of A times the infinity norm of A, that is by P2. That is by P squared infinity norm of A cubed. All calculations done. And so we see that the infinity norm of A cubed is bounded by P squared, infinity norm of A all cubed. We will be inspired by this. And suppose that at order K, we have the relation, the inequality, infinity norm of A to the power of K bounded by P to the power of K minus 1, infinity norm of A to the power of K. Then at order K plus 1, we have the infinity norm of A to the power of K plus 1. A to the power of K plus 1 is written as a to the power of K times A. So we can say that it is bounded by P. We need the infinity norm of A to the power of K times the infinity norm of A. And using the recurrence hypothesis, we find P to the power of K, infinity norm of A, all to the power of K plus 1. So we can conclude that for any n greater than 1 in A, the infinity norm of A to the power of n is bounded by P to the power of n minus 1 times the infinity norm of A to the power of n. Now, let's study the nature of the proposed matrix series. We will bound the norm of its general term. Thanks to the previous relation, the norm of this term, the infinity norm, is bounded by 1 over factorial n, positive, consistent with the norm. And the infinity norm of A to the power of n is bounded by P to the power of n minus 1, infinity norm of A, all to the power of n. We have thus bounded the norm of the general term of this matrix series by the general term of a numerical series. Let's study the nature of this numerical series. Given the factorial and the powers, we will apply D'Alembert's rule or the quotient rule to it. Here then, if u1 equals 1 over factorial np to the power of minus 1, infinity norm over to the power of n, then the absolute value of u1 plus 1 over u1, of course, we assume 1 is null, otherwise the series is obviously convergent. So u1 plus 1 is 1 over factorial n plus 1 p to the power of n, infinity norm of a to the power of n plus 1 times the inverse of u1, that is 1 factorial n times p to the power of minus n minus 1 times the infinity norm of a to the power of minus n. Then the factorial simplify, leaving n plus a at the bottom. The powers of p simplify to ap. Power times p to the power of do minus, again, that makes pn. The infinity norms of a simplify to infinity norm of a to the power of n plus 1 times infinity norm of a to the power of minus n. It gives exactly the infinity norm of a. P and the infinity norm of a being constants. When we let n tend towards infinity, we see that the limit of the absolute value of n plus 1 over n is 0. So, this limit being strictly less than 1, D'Alembert's rule states that the numerical series is convergent. Therefore, the series of matrices is absolutely convergent. And we can conclude that it is therefore convergent. It is enough to recall that the space MP2, minute of this norm and of dimension finite P2. In fact, it is homomorphic to a power P2, minute of the infinite norm, which is complete, thus our space being complete. The absolute convergence implies convergence, and therefore the series of matrices is convergent. Third question. In this third question, we will assume that the norm of the matrix M, the new norm, is strictly less than 1 and show that IM is invertible. For this, we will use the identity IM to the power of n plus 1. We can write it as IM. The sum from k equals 0 to n of m to the power of k. Here is the partial sum of the series. We will play with the powers of m, powers of m From the relation norm of A, B is less than or equal to the norm of A times the norm of B. We see that if A is equal to B, we obtain the norm of A squared bounded by the norm of A, all squared. And thus we can easily establish by induction that the norm of M to the power of n is bounded by the norm of M to the power of n. This is the advantage of matrix norms. Since we know that the norm of M is strictly less than 1, the limit of this real number, the norm of M to the power of n, is 0. We deduce that the limit of the positive term it bounds is also 0. Now this is the norm of the vector M to the power of n, the matrix M to the power of n. And so if the limit of the norm is 0, the limit of the vector is 0, or it is the matrix 0, we can clearly see that if we return to the identity we have written at the beginning, if in this identity we let n tend towards infinity, we see that n plus 1 will tend towards 0, and the first term tends towards in. The second term contains the factor I minus total m, which does not change, and the partial sum, which must tend towards n. The sum from k equals 0 to infinity of m to the power of k. So this equality, therefore, which is true, is an equality between matrices, as long as both terms are well defined, which proves both that A minus Mr. is invertible, since by multiplying it by this sum, we find the identity. Notice that it is common, since only m is involved in it. And at the same time, the series sigma from k equals 0 to infinity m. Power k is convergent, and its sum is exactly the inverse of I minus m. Here are some other calculations, in a normed vector space, and a brief note on matrix norms. Thank you.